newly released satellite imagery, and official strike footage present a clear, verifiable picture of a precision attack on the Jacobabad power and energy node that underpins Pakistan Air Force operations, paired with visible hangar and runway damage at multiple Pakistani air bases during Operation Sindoor. And the effects are overt, high contrast, and operationally decisive. At Jacobabad, the before and after sequence isolates a critical power distribution hub servicing the air base ecosystem, and the impact signature shows a distinct, ground-level detonation with a pronounced crater, debris dispersion, and structural impairment consistent with a unitary precision weapon designed to disable surface infrastructure rather than burrow for a subsurface blast. The functional takeaway is straightforward. Striking a utility node that routes electrical power across maintenance bays, lighting systems, pumps, and communications imposes immediate constraints on sortie generation and base recovery timelines. In the released frames, the geometry of the blast zone and the pattern of secondary ejecta point to a direct utility denial effect, aligning with a broader set of curated releases showing multiple, discrete desired mean points of impact on adjacent operational assets. The official narrative around the new footage frames a tightly scoped, coercive operation employing fewer than 50 precision weapons to terminate the crisis, an economy of force approach that hinges on selecting high payoff nodes and demonstrating verifiable impact. In the public briefings and curated clips, runway cratering sequences and structural strikes are synchronized with third-party satellite assessments to create a transparent evidentiary chain. Official release, commercial imagery confirmation, and open-source geolocation and measurement. That triangulation is deliberate. It replaces inference-heavy assessments with plainly visible, externally auditable damage signatures. Runway craters measured at several meters in diameter, hangar roof collapse zones, burn scars, and debris fields that are legible even to non-specialists. Within that evidentiary architecture, Jacobabad's energy center is the archetype of utility denial. By removing the power node, even intact shelters and aprons face degraded functionality. Night operations are slowed or halted. Maintenance cycles lengthen. Fueling and pumping timelines stretch. Emergency power contingencies, if present, must be prioritized against a suddenly wider array of demands, introducing operational friction at exactly the moment recovery is most critical. In parallel, the same public release set includes hangar and apron strikes at Jacobabad that compound the denial. Structural deformation and roof failure diminish shelterability, while debris management and safety checks absorb manpower and time. Indian Air Force also destroyed this radar at Jacobabad. A RAC-3D radar sighted on the base periphery, confirmed in the Vice Chief of the Air Staff's briefing image that labels the radar head and shows the precise point of impact in the after frame, known as RAC-3D radar. Flamingo is a mobile, three-dimensional, planar phased array surveillance and coordination radar operating in the G or H band with an instrumented range up to 100 kilometers, optimized for detecting low-altitude and low-observable targets in heavy ground clutter. Capability highlights include three-dimensional air picture generation to 100 kilometers, elevation coverage greater than 45 degrees, integrated identification friend or foe with secure modes, rapid deploy and stow in about 15 minutes with a two-person crew, mast elevation to approximately 13 meters for improved low-level line of sight, standalone or networked operation, and weapon queuing for very short-range air defense and short-range air defense units. Pakistan Air Force employs RAC three-dimensional within layered air defense, including as a gap filler and as the organic surveillance and alert radar for systems such as the Spada 2000 battery, where it can track around 100 targets and coordinate multiple firing units in its sector. Impact of this kill at Jacobabad is immediate. The recognized air picture around the base loses a local three-dimensional surveillance node, reducing low-altitude detection ranges, degrading track continuity and identification friend or foe correlation, and slowing queuing of surface-to-air missile units and anti-aircraft artillery sections tasked to protect the airfield and its approaches. Operational effects include longer detection-to-intercept timelines for fighter scrambles, increased reliance on more distant sector radars that introduce latency and azimuth gaps, and higher burden on patrol aircraft to compensate for the lost sensor coverage during runway repair and sortie generation. The strike evidence shows a precise desired mean point of impact on the radar pad, producing surface scarring and debris dispersion consistent with a unitary precision weapon intended to neutralize a fixed sensor without broad-area damage, matching the measured, point-target pattern documented across Operation Sindoor. Acquisition context and price. RAC 3-dimensional is a Thales Raytheon Systems product fielded in multiple European services with more than 50 systems produced. Procurement encompasses the radar shelter, mass system, command posts, training, spares, and site works. While per-unit contract figures vary by configuration, open-source program notes emphasize that these are high-value sensors whose replacement entails not only the radar, but also civil works, integration, and recertification costs that materially exceed the hardware alone. Process and time to reconstitute after a loss like Jacobabad generally require surveying and preparing a new pad or reconditioning the damaged site, transporting and erecting a replacement radar, integrating communications with the sector command network, recalibrating clutter maps and identification friend or foe overlays, and requalifying crews. Even within service spares, this can take weeks to months depending on logistics and the availability of another deployable set. Bottom line, neutralizing the RAC 3-dimensional radar at Jacobabad removes a cornerstone of local early warning and weapon queuing, compresses the defender's decision window, forces dependence on less optimal sensors, and imposes a costly, time-consuming recovery cycle to restore pre-strike coverage and command and control fidelity. The video released by the Vice Chief of the Air Staff documents the use of the crystal maze precision-guided munition by the Indian Air Force against a terrorist compound during Operation Sindoor. The visuals show the Muridke headquarters, home to the Lashkar-e-Taiba organization, and highlight 4 intelligence-identified positions, the administrative building and residences occupied by top leadership. Crystal Maze, also known as the Popeye air-to-surface missile, is an Israeli long-range standoff weapon equipped with an advanced imaging infrared and television seeker, offering highly accurate target engagement at ranges up to 80 kilometers. The missile is capable of striking well-defended, high-value targets with pre-programmed guidance, man-in-the-loop terminal control, and the ability to abort or redirect mid-flight if needed. In the technical battle damage assessment shown in the video, the munition can be seen creating a sharp, precise entry hole on the roof of the target building, with no accompanying external blast or widespread structural damage captured in the immediate overhead footage. This reflects the crystal maze's capability for pinpoint precision and internally focused destructive power, minimizing collateral effects. However, despite the minimal visible damage from above, follow-up local onlooker videos confirmed that the weapon's deep-penetrating warhead caused catastrophic internal destruction, collapsing floors and neutralizing the compound from within. This demonstrates both the missile's effectiveness in breaching hardened structures and the Indian Air Force's ability to independently verify impact accuracy and strike outcomes using real-time electro-optical video for precise battle damage assessment. The newly released strike clips add an indispensable dimension. Motion, thermal contrast, and plume analysis help corroborate the type of detonation and the hit location on the structure or surface. When combined with commercial satellite imagery captured within days, the clips provide multi-sensor, multi-temporal validation. The cadence of release, official frames, amplified by national media packages, and then distilled by open-source analysts, helps close typical gaps between classified battle damage assessment and public evidence. That cadence minimizes ambiguity, accelerates independent verification, and places the burden of refutation on those disputing what is plainly visible. The contrast with the 2019 Balakot debate is stark. Then, public contention focused on limited visible roof penetrations, small diameter entry points attributed to penetrator warheads intended to deliver internal blast effects with minimal external scarring. Those signatures were subtle in overhead imagery. Roofs appeared intact to casual observers, even if internal structural damage was plausible. That visibility dilemma fueled arguments over whether damage truly occurred at meaningful scale. Analysts had to lean on weapon physics, probable fuse settings, and interior blast modeling, all of which are harder to communicate to lay audiences and easier to contest in the public arena. This time, the signature speaks for itself. Roof collapses on shelters are unmissable in before, after frames. Burn and debris signatures radiate from the point of impact in recognizable patterns. The Jacobabad energy node crater, in particular, provides the sort of high-contrast, high-confidence evidence that compresses the verification cycle. It is a hole where there was none before, surrounded by dispersion that matches a surface detonation at a utilitarian structure. The operational implication is equally immediate. Deny power, deny function. No need to argue over interior blast propagation when the grid node is evidently severed. Operationally, the presentation underscores a calibrated campaign design. Target selection is coherent across 3 functional lines: runway interdiction to pause flight operations, shelter and hangar strikes to degrade aircraft availability and maintenance throughput, and utility node attacks to stress the base's backbone systems. Each category imposes a different recovery burden. Filling runway craters demands specialized materials and teams. Hangar repairs involve structural assessment and safety certification, and power restoration requires redundancy management and load balancing. Together, they compound delays and complicate the defender's prioritization matrix. With fewer than 50 precision weapons, those effects can be distributed across a network of bases, magnifying coercive impact while limiting overall escalation. It communicates both capability and restraint, the capacity to put holes exactly where they matter operationally, and the choice to stop once the coercive effect manifests. In the narrative frame, the new footage and imagery also bridge the trust gap that often opens in information operations. By enabling the public to see what analysts see, craters, collapse, scorch, authorities reduce the interpretive burden that once plagued discussions like Balakot. The apparent intent is not merely to claim success, but to make the claim minimally contestable through shared observation. For the information environment, that lowers noise and accelerates consensus, especially when third-party imagery vendors capture similar scenes within days. Finally, the broader implication of the Jacobabad energy node strike is about leverage. Utility nodes multiply the effect of each weapon by reaching into every depth. Indent system. In a campaign built on limited salvos, leverage is the currency of success, striking where a single point of failure constrains many downstream functions. By pairing that with runway and hangar impacts, the released material depicts a layered denial architecture. Remove power to slow everything, crater runways to halt launches, and degrade shelters to complicate aircraft generation. The evidence is visually clear, independently verifiable, and operationally coherent, and it directly answers the critiques that once hinged on subtle roof perforations and invisible interior damage.